Hey guys, today we're going to focus on identifying intercepts, both graphically and algebraically. What's really nice about today's topic is this process works just as well for super complex functions as it does for really simple, linear functions. It's kind of a trick that you're going to put in your bag and pull out from time to time over the next several years. And I can't tell you how many times I found myself in a pickle with a really complex function, and I didn't really know where to go. But then I said, why don't I see what the intercepts are? And then all of a sudden, once I know the y-intercept and the x-intercept, I'm able to kind of get the ball rolling and kind of wiggle my way through that problem. So in this video today, graphically, we're going to say, just by looking at the graph, can we identify the y-intercept as well as, in this case, the three x-intercepts? So I think that's going to be a real cupcake. And then it may get a little more challenging, saying instead of a graph, what if we give you the equation? Can you find both all the x-intercepts and the y-intercept? I promise it's easier than you might be thinking right now. Here we go. So what is an x-intercept? Let's make sure we all agree on this. They are points at which the graph crosses the x-axis, all right? These are often called the zeros of the function, and a lot of times they may take a function and set it equal to 0, and they may just say solve without saying find the x-intercepts, and we could say, okay, anytime we set this function equal to 0, we're finding the x-intercepts, whether they explicitly say it or not. Now, it is possible for a function to have more than one x-intercept, okay? Now, it's possible that a function has no x-intercepts. We've seen quadratic functions that never cross the x-axis, but it's also possible to have more than one. And the value of y at any of these x-intercepts is guaranteed to be 0, which is a really nice guarantee that we're going to tap into. And then, of course, what is a y-intercept? Well, that's the point at which the graph crosses the x-axis. Worth noting here is I am using the singular sense of that word as opposed to the plural, because a function, if it's a function, it could have at most one y-intercept. Now, there are going to be some equations that aren't functions, like, believe it or not, like circles. Circles are not functions because they fail the vertical line test. So a circle or an ellipse or some type of other conic like that could have more than one y-intercept, and I think we'll see one at the end of the video tonight. And then worth noting here is the value of x at any of these y-intercepts is guaranteed to be 0, and we'll tap into that before today's over. All right, so can we identify all the intercepts? Why don't we start with the one y-intercept that we're seeing here? So it looks like we're crossing the y-axis at 12. So I'm going to simply say y equals 12 as an intercept. And then it looks like we've got three x-intercepts, maybe -5, -2, +3. We'll list all of those bears here. X equals -5, x equals -2, x equals 3. Now, worth noting is we do have a bounce right here. So this root right here would have a multiplicity of 2 because of that bounce. It is a fourth degree polynomial. We've got a singular root there, a double, and then a singular one. So we technically have 4 roots, even though only 3 of them are visible, and this would be a fourth degree polynomial. Okay, given this equation, it is a linear equation, can we find the x-intercepts and the y-intercepts? So here's how I always want to break in. This is how I organize my thoughts. I kind of draw myself 2 boxes like this, and if I want to find the x-intercepts, I'm just going to substitute a 0 for y. So it would look like 4x plus 6 times 0 plus 12 equals 0. We know those are going to cancel. 4x plus 12 equals 0. Why don't we subtract 12, divide by 4, and we're going to get x equals -3. Bingo, bingo. And again, I'm really willing to bet that you felt totally comfortable doing all of that in your head. I'm okay with that. Now let's find the y-intercept. We're just going to substitute the 0 for x. So we got 4 times 0 plus 6y plus 12. We know these bears are going to cancel. So we've got 6y plus 12 equals 0. We could subtract the 12, divide by 6. And again, if you feel comfortable doing that in your head, feel free to do so. You're going to be amazed at how you could get into some really, really complex functions and all of a sudden just mentally find those x and y intercepts just by literally looking at the equation. All right. This one's slightly more challenging for sure. So for those x-intercepts, and I would say 90% of the time, at least, the x-intercepts are more challenging than the y-intercepts. We're going to substitute a 0 for y, which is this f of x guy. So we'll say 0 equals 2x squared plus 7x minus 4. Now you'll notice we're working with a quadratic function instead of a linear function like we were in the last example. So now your go-to method is factoring. And this is going to be factoring with what I like to call a little guess and check, a little trial and error. The multiples of 2x squared are going to be 2x times x. Now what you got to do is you got to kind of play around with those multiples of negative 4 until you get them to fit just right. I'm going to put a positive 4 here and a negative 1 here. And the reason that works is because the product there is 8x, the product on the inside is negative x, and adding them together makes this positive 7x that we have in the middle. So anyway, I'm going to go ahead and erase that little tidbit. Because what I want to do now, once it's all factored, we're going to do what we've done a million times. We're going to just tee this bear up. We're going to set each one of these factors individually equal to 0. And you're going to get x equals 1/2 as an x-intercept and x equals negative 4 as an x-intercept. And again, a second degree polynomial, you're expecting 2 x-intercepts. It's kind of a giveaway there. Now, as far as that y-intercept, we're going to substitute the 0 for x. You could say f of x equals or y equals. And I'll tell you what, there's not many better things than substituting 0 for x. We know this bear is going to cancel, this bear is going to cancel, and you're just going to get negative 4 for your 1 y-intercept. All right. We're going to finish with a bigger bear, and we do have more of a circular type of conic here. And the reason we are anticipating a circle is because notice the squared signs, we're squaring the x, but we're also squaring the y, and that's what makes it circular. So we're going to have some more work to do. This is about as hard as the problems are going to get. The x-intercepts, let's go ahead and substitute the 0 for y. X squared plus 6x plus 0 squared minus 9 times 0 plus 8 equals 0. So good news here, we're going to see these two terms cancel. We're left with x squared plus 6x plus 8. We do have a quadratic on our hands, and with a little bit of luck, this bear is going to factor. We could tee that up and get x equals negative 4 and x equals negative 2 as my 2 x-intercepts. And then shifting over here for the y-intercept, substituting a 0 for x. So now we got 0 squared plus 6 times 0 plus y squared minus 9y plus 8 equals 0. We'll cancel, cancel. We're sitting on y squared minus 9y plus 8. Factor that bear. Oh boy, does it factor? Does it factor? Fingers crossed, fingers crossed. I'm feeling like negative 8 and negative 1. Tee that bear up. We'll get y equals 8, y equals 1. Oh, I don't know if you just saw that. My laptop's tweaking out. Probably doing too much math here today. It's starting to smoke. So anyway, you're probably wondering, why are there 2 y-intercepts? Again, earlier we said if it's a function, it can't have more than 1. Well, again, this is an equation. Like we said, it's kind of circular. And when you go to graph it, it's probably going to fail. In fact, we can guarantee it. You know, you picture this. Let's just say, okay, here's x-intercept negative 2. Then we go over. Oops, we got to go this way, negative 4. Wow. I started graphing that by hand, and I said, it may not work out the best. So what I got is, let's go to Desmos here. I just typed in that same equation that we just started with here in Desmos, and you could see right here how you've got these x-intercepts of negative 4, negative 2, y-intercept of 1 and 8, just like we had. And again, it's a really nice circle that does fail the vertical line test, so it's not a function, but that's okay. We found all the intercepts that we needed to find. All right, that's it for intercepts, and I promise you, just take these ideas, stick them in your back pocket, and you'll be amazed at how often you use these over the next 3 to 4 years, I bet. Have a great night.